you can see this proof, but I will explain it in slightly more simplified way, and I will begin. So, there are two statements. First, if we have a self-similar set, I will show you the page in larger size. Oh. This way. Yes, if you have a self-similar set, he has different notation. Yes, for his self-similar set is fractal, so he denotes by F. Yes, and if the open set condition holds for these self-similar sets, then Hausdorff dimension and box dimension coincide with the similarity dimension of this system. And moreover, for this value of S, Hausdorff measure is positive and finite. So I will do all this job, explaining and showing you the pictures. So, one part was shown initially. So, if you have K is equal to union of Si of K, then if K is union of Si of K, then for any delta, the sets Si1 In of K where I1 In are chosen such that Q I1 In is less than delta, less or equal than delta, and Q I1 In minus 1 is greater than delta, then this set form a delta covering of K. Yes? Oh, sorry, maybe I will do it in slightly different way, because this choice will be made where N is chosen such that Q maximal to the power of N is less than or equal than delta. So I will make them of different size, but all the sizes of these copies will be, so I take, in the case when the copies have different size, I will take such N that the largest nth iteration of the largest copy is less than delta, so all these copies will form a delta covering of K. These sets form a delta covering of K. Therefore, the sum, so let S be the similarity dimension of K of the system S. System S. It means that Q1 to the power of S plus Qm to the power of S equals 1, right? Then the sum of Qi1, the sum of diameters of Si1 In of K to the power of S will be less or will be equal to diameter of K to the power of S multiplied by the sum Qi1 In to the power of S, but this sum can be transformed in the way that it will be K to the power of S multiplied by Qi1 to the power of S plus Qm to the power of S to the power of N, right? And this sum is equal to 1. Therefore, we have for each delta covering, there is a delta covering of K such the sum of diameters of the elements of delta covering to the power of S is less than the sum, yes, is equal to the K to the power of S. So we have a delta covering of K, yes, and the diameters of the elements of delta covering, when we take S power of these diameters, sum up to Ks. But what can we say about Hausdorff dimension? Hausdorff dimension. Hausdorff dimension of S of K is a do you remember how we define the Hausdorff dimension? We take Hausdorff measure or Hausdorff content, and we take the minimal number for which Hausdorff content is equal to 0. Yes. But if this sum is equal to Ks, then Hausdorff content is more or equal to 0. So the dimension of K should be less than S. Yes. So from that it follows that Hausdorff dimension of K is less or equal than S. So this thing I already explained, and it is quite simple. But we need to prove the other inequality, that Hausdorff dimension of K is greater or equal than S. Can I continue? So, you see, I just repeated this excerpt because I explained it earlier, and it doesn't use the open set condition, but we need to use the open set condition. Yes, it will be the argument showing that Hausdorff dimension of K is greater or equal than S. Yes, needs more. It uses it first. It appeared in Hutchinson's paper, Fractals and Self-Similarity. Yes, and this way of thinking became classical, and I will explain it. So I proved the other side, yes, the other inequality. Let S satisfy the open set condition. Not long ago, I explained to you the mass distribution principle. The mass distribution principle. So if, how it sounds, it sounds the following way. If there is mass distribution principle looks the following way. If there is a measure on X, such measure, positive finite measure, such that mu of x is not zero and is less than infinity, and it is, for example, equal to some m. Yes, and for any ball BR in X, the measure of BR, oh sorry, this, okay, measure of BR is less than CR to the power of S, is less or equal than CR for some constant such that mu of x equal to m, and for any ball Br of x, mu r of Br is less or equal than C multiplied by R to the power of S, then Hs of yes, Hs of x, sorry, I forgot, is less than what? What? I don't hear. Yes. Is Hs of x is more than mu of x divided by C. Yes. Okay. Hs of x is more than mu. So I mean mu of x divided by C. Okay, therefore, since the Hausdorff S-dimensional Hausdorff measure of x is more than mu of x divided by C, then the dimension of x is again I'm mixing. If mu of x, Hs of x is more than m, the dimension of Hausdorff dimension of x is so we have opposite. Here we had less. Okay, then Hausdorff dimension of x, Hausdorff dimension of x is, greater than S. Greater than S. So this is a mass distribution principle, and we will base on this mass distribution principle an open set condition to prove that Hausdorff dimension of x is equal to S. Okay. I want to say several words about open set condition. Can I erase this part? Okay. I want to say some words about the open set condition. So if the open set condition is satisfied, then we have such an open set O that Si of O lie in O and they don't intersect. This we know very well. Yes. So if we have, so for any I not equal to J, Si of O intersection Sj of O is empty. If we take any family of tuples Si1In and if you have two tuples Si1In and J1Jm such that they are non-comparable, it means that this this is not a prefix, first is not a prefix of second, and second is not a prefix of first, then if are non-comparable, then Si1 In of O and Sj1 Jm of O will have empty intersection. So if we have these sets, then we have this sets second iteration of V of O, and further all these sets have the only relation: either one lies in the other and the multi-indices are comparable, or they don't intersect. Therefore, we can consider very interesting families. How to call it? Given a number rho more than 0, we can consider a family of such multi-indices I1, In, the n may be different, such that Q I1 In is less or equal than rho, and Q I1 In minus 1 In minus 1 is greater than rho. So what does it mean? What does such family means? We have copies of different size, right? So the size of these copies is, suppose that the diameter of K is 1. So we consider only those copies whose size is less than rho, whose diameter is less than rho, and their previous ones, when we truncate this number, are greater than rho. So they are approximately of the same size. So we consider such family. And further works also use these families. And in terms of these families, the weak separation property is also formulated. Okay. Maybe I will denote it by Q rho. So if I consider this family, we have one very interesting relation. So rho Q I1 In is less or equal than rho, and from the other side Q I1 In is greater than rho multiplied by the minimal Q, right? So from this definition of this family, for each of these elements we have the following relation. This is the first. Second, very interesting, if we have any of elements of this family, then they are not comparable, yes? Because if we have some element, we have some multi-index, then its prefix doesn't come to this family, right? So for any two elements qi1 im qj1 j i1 in qj1 jm, these two elements will be elements, excuse me for my pronunciations. These two elements will be not comparable. First, all indices I1, In in Q are not comparable. At the same time, we have that K is equal to the union of SI In of K, where I1, In belong to Q rho, right? Because for any copy, so if we take any point, then it is the intersection of nested copies, yes? So it will be QI1, QI1I2, QI1IN, right? And in this sequence, there is only one element from this family, right? So therefore, K belongs to this union, yes? And from the other side, when we have the elements of this union, any O, Si of O and Sj of O do not intersect, yes? And for any I and J, I draw bold-faced letters for multi-indices or for tuples in Q rho. Si of O intersection Sj of O is empty. So very nice family. Because if we consider this family, then its images under this family cover the whole row, and at the same time the images of the open set do not intersect. Please notice one fact, that K belongs to the closure of the open set. Why this is so? You would ask me why this is so. You see, S1 union Sm of O, Sn of M, Sm of O lies in O, right? When we come to the closures, it happens the same way, yes? Yes. Therefore, the iterations of O converge to K, and you see, so if I write this operator as T, we have T of O belong to O, so O contains T of O, and Tn of O converge to K, right? Therefore, each of these sets contains K. One second. What? Oh, we have a break in 15 minutes, right? Okay. Because I am adapted to 45 minutes, then break, then 45 minutes. So as 45 minutes are finished, I feel that I need to make a break. But it is a wrong feeling. So we defined this family Q-ρ, and we established its very nice properties. So we keep in mind the K satisfies the open set condition, and this open set condition, when they are grouped in such families, images of the open set, when they are grouped in such families, are very well manageable. Yes, because they are almost of the same size, do not intersect, but their closures in common cover the whole K. Of course, if the contraction ratios are equal, such as in Sierpinski gasket, then there is no problem. We just take the copies of nth order, and all they are good. Yes, but if the copies have different sizes, then we need to make changes. There is one more model which is used in while we manage the self-similar sets. It is the following. So we have a projection of the index space to K, right? It's a address map. We considered the address space, yes, the space of infinite sequences, and we introduced a matrix on it. And this matrix turns the index space to a compact self-similar set. If this matrix coincides, the coefficient defining this matrix coincide with the Q1, Qm, then this self-similar set have the same similarity ratios as K, but with only difference that copies do not intersect. It is very well organized, yes. But I suppose I need to install or define an S-dimensional measure on this set of infinite sequences. How we measure? So you know that if we have I infinity, it is the union of sigma 1 of I infinity, sigma 2 of I infinity, and sigma n m of I infinity, where sigma of I1, sigma k of I1, I2, I3 at infinity, so it is a k I1, I2, I3. So sigma k is the operation which puts number k in the very beginning of the sequence. Yes. So I infinity is disjoint union of these sets, and these sets are usually called cylinders. Yes. And for any n, I infinity is a disjoint union of sigma I1 In of I infinity, right? So, for example, if I is equal to 2, we have sequences of symbols 1 and 2, yes? So, this set is divided into two parts. One part is a set of symbols beginning with 1, and the second part is the set of symbols, symbolic sequences beginning with 2, yes? But it can be also subdivided into the 1 I infinity, union 1, 2 I infinity, union 2, 1 I infinity, and union 2, 2 I infinity. Sorry, do I speak sufficiently loud now? No? Yes? Because I begin to speak in very 2 I infinity. Yes? So we have a sequence of how to key. So a sequence we take I infinity and divide it in several parts, then divide. So we have a sequence of subdivisions of I infinity, which such that diameters of these elements of this subdivision turn to 0. Therefore, we can define the measure of I infinity in the following way. So you have I infinity, and it is divided in several parts, then it is divided in several parts. If we define the measure of each of these subdivisions, then we define the measure of I infinity. Yes? Because any set can be, any open set here can be represented as a union of such cylinders of different size, yes, and this will be always a disjoint union. So the measures of these cylinders will sum up to the measure of A. Okay, so we define the measure on I infinity in the following way. If we define a measure of each cylinder, then it's okay. So we have the system S1 SM. As far as I remember, we consider the system S1 SM. Yes? And the elements, the contraction ratios of these similarities are Q1, QM. And the sum of Q1 to the power of S, Qm to the power of S equals 1. Right? Therefore, And for any n, qi1 in, the sum of qi1 in to the power s also equals 1. We proved it. Very good. Then we have I infinity, and we define a measure on it the following way. The measure of sigma I1 in I infinity will be equal to qi1 in to the power of s. So we divided I infinity to m parts, and the sum of measures of these parts equals 1, yes? And then each of these parts is divided in m parts, and the sum of their measures is the measure of this whole part, yes? So we get a probability measure of I infinity, yes? Do you feel any kind of protest against my words now, Vijay? We have 5 minutes till the break. So we define the probability measure, and it is a natural measure. Yes, because the measure of each cylinder is the following one. So it's very good. It's very good measure. It is self-similar, because when we apply a similarity with ratio q, then the measure is diminished q to the power of s times. Okay. So it is a natural measure on I infinity. Yes, it is natural. Then so I take this I infinity with its natural measure and project it to k. So I have I infinity supplied by the measure mu, and I have a projection pi of I infinity to k. Yes. If we map one set to the other, and the first set contains some measures, so this measure is projected to the other set. Then we defined some subset, then the measure, so it will be the measure mu with this wave. Mu of A is equal to the natural measure of its preimage under pi. Mu of pi minus 1 of A. So, and this will be also a very good measure on A, because it will be you see that mu of Si of A will be equal, so not equal, because there will be overlap between copies, so it will be more or equal than qi to the power of s, qi to the power of s multiplied by mu of A. So we defined a very special measure, which is the image of a probability measure on I infinity, and we put it on our set K, and we will use this measure we'll try to apply mass distribution principle to this measure. Yes. Okay. And it will be after the break. One question, sorry. Who knows this proof well? And who knows this proof a bit? Slightly, okay. And you too, yes, okay. But with the course of time, many years ago, it looked for me very simple. but now it looks for me quite complex. I don't know why, but maybe because of its connections with other proofs. Mm-hmm. Today is Friday. Sorry. Wow. Oh, yes. Thank you. Thank you very much. You saved me. Yes. Oh. I would like to show you one picture which I promised to show you yesterday, but couldn't find because of very small font. I could not recognize. This is the example which I discussed yesterday. You see? This is a dendrite. Yes? This is a dendrite. And here you have 1, 2, 3, 4, 5, 6 copies of this dendrite, and they intersect in this black subdendrite. So how it was constructed? I had some kind of family of hexagons, but it can be extended to a family of pentagons with regular pentagons with 12 sides. So this dendrite is a subdendrite of a large dendrite with 12 branches, yes? So if we take this initial one and properly rotate its copies here we'll have the images of these copies will just sum up to this 12-sided, 12-branched dendrite, yes? But they are organized in such a way that they intersect in this subdendrite with 6 branches. So such is a nice construction, but I will explain to you how you can construct dendrites from polygons. So suppose you have a triangle, yes? If you have a triangle, you can draw some number of triangles inside it, yes? In such a way that any of them have one common point. And this point is a vertex. Yes, then if you take the system S1, S2, S3, and S4, which sends the larger triangle to triangle 1, 2, 3, and 4, yes, then the attractor of this system will lie inside this triangle, first. Second, the vertices will belong to the attractor. The attractor will be connected because the intersection graph is connected, and it will be a dendrite because the intersection graph is a tree, right? The attractor will be a dendrite. So initially it was proved in more complicated manner, but now it is very, as usual, everything becomes simple with the course of time, except the theorem about open set condition. Okay, so we can construct such a system, yes, and build its attractor. But if you have a dendrite, in a dendrite, only 2 points can be connected by unique arc. So if we connect the vertices of the triangle by this arc, we'll get a main tree of this dendrite. It is a main tree. Maybe this picture is quite complicated, but if you consider a Dirichlet set, you see the Dirichlet set, which is formed by 5 maps, 5 homotopes, which send the square to small squares. Yes. Then you will see that the main tree will be such a cross. Yes. And if you consider the images of this main tree, then you will have the images of this cross, many, so it will remind us the graph of a group, yes, of okay, so if you consider this main tree will, the images of this main tree will cover the whole set of cut points in the dendrite. Because if you have a dendrite, there are 2 kinds of points. There are endpoints and cut points. It's very interesting. What is the dimension of this figure? Can you find the dimension of this set? Suppose that all these numbers are 1/3, 1/3, 1/3, right? So you have 5 copies with coefficient of 1/3, and 5 multiplied by 1/3 to the power of s should be equal to 1, right? Therefore, 3 to the power of s is equal to 5, and s is logarithm of 5 with respect to 3. So dimension can be found quite easily in this case, because this is a very special case in which dimension is easy to find. Okay. Now, and what's about the main tree? The main tree consists of straight lines, right? Therefore, if we have a main tree and if we take the set of cut points in this dendrite, it will be a countable union of these lines, right? Therefore, it has dimension 1. You see, the dimension of the main tree is equal to 1, and dimension of the whole dendrite is equal to logarithm of 5 with respect to 3. So this dendrite is easy to be constructed, yes, and we can you try to do this? Is it possible for you to create this picture in your laptops? Or do you have such a possibility? Or you are deprived of this possibility? You have no laptop.
It's okay, we can manage.
Huh?
We can manage.
Oh yes, together it will be easier to do everything. So just try to construct what are you thinking about?
No, nothing.
Do you need any help in constructing these maps? So you have a polygon, yes, and you have its image. So maps are very simple, right? So what is this map? S1 of x. So if this is 0, this is 1, 0, and this is 1, 1, and this is 0, 1, yes? So S1 of x will be x divided by 3, right? And all the others will be obtained from this x divided by 3 by translation. So you can write that k equals what? 1/3 multiplied by union identity union 2 0 because this 2/3 2/3 yes union 0 2 union 2 2 and union 1 1 1 1 multiplied by k. Am I right? Okay. So maybe the number smaller. For assignments, it's too much. It's okay? Yes. Yes. But how to build this main tree? The main tree is a more complicated thing because it consists of several arcs. You see, this arc and this arc. In this case, these are two arcs. Yes? Yes, it is easy because these are lines and this is not a problem. But now let us consider the second example. I take a triangle, yes, take some Q, take some q, it is the same, and then draw this one triangle inside, yes? How to construct this attractor? So you need to compute these points, right? These points. And you need to compute this rotation. So you need to know this interval, yes? And if you take this 1, 0, 0, and 1, 0, yes? So you need to define the map which sends this interval to this, 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 and this. So first you need to find these three coordinates, and you need to know this coordinate and this, the length of this, and the coordinates of this interval, yes? Right? Okay. So, can you find these numbers? So if you have q, you have q, and you have this. Do you need help, or it's easy for you to find these numbers? So let us look. This point is 0, 0. This is, what is this coordinate? Q0. Right? What is this coordinate? Can you find this one? This is q divided by 2, so first coordinate is 1 minus q divided by 2, and second, q square root of 3 divided by 2, right? And also we need this point. This point, what it will be? 1 minus q multiplied by square root of, 1 minus q, 1 minus q divided by 2, right? And 1 minus q, you have, do you see? This is not a vertical, so this point has, you have 60 degrees angle, yes? This is, the length of this interval is 1, and the length of this one is 1 minus q, because this is q. So it will be 1 minus q divided by 2. And this coordinate will be 1 minus q multiplied by square root of 3 divided by 2. Yes? So you have these coordinates. And these coordinates, you know this coordinate? Yes? This you know, this one you know. It's 1 minus q0. Q0. So let us draw the system. What system will give us this attractor? So this triangle is contracted q times. So you will have k equals q sorry, first we need to write translations. 1 minus q 0, and this coordinate y minus q divided by 2, 1 minus q divided by 2 square root of 3. Yes, and it will be multiplied by q. And this map is a map which sends 0, 0, 1, 0 to these 2 points, right? These 2 points. So it will be SIM, and you take this coordinates q0 and this one SIM of q0, what 1 minus q divided by 2, 1 minus q divided by 2, 1 minus q divided by 2, and q square root of 3 divided by 2. And if you write this way, then you will get the attractor. Yes? So please, of course you need to define q. So q will be a number. This number will be real. And it's better if it's less than 1/2 and more than 0. But let us take it between 0 and say 0.4. Zero is too small. Let it be between 0.1 and 0.4. Not very small and not very great, because if you put the value 0, sometimes you will get the number is chosen randomly, therefore some pictures will be not good. So we suppose to give you some assignments today in the evening so that you could do it till tomorrow. And this will be assignments to build something, to build some models, and to find dimensions or find equations for them if So is that okay? It's very interesting, yes. If you have some problems, I will, after you construct this example, then we'll discuss one more question concerning this self-similar set. Does it work? What?
Showing no errors, but when applied it is not showing up.
Yes. The problem is that where is your equation? 1 minus q0, 1 minus q divided by 2, 1 minus q multiplied by 3 to the power 1/2 divided by 2, it's okay, multiplied by q, and SIM and q, and what it is not shown up. Okay. Because I said it must be between 0.1 and 0.4. If you take 0, it cannot construct anything because the mappings will not be contractions. Yes, nobody knows what danger. Sorry. Yes, again. No, it doesn't show. 1 second. Wow. How did you? Yes, it's like this, yes. But I have more interesting problem. The main problem is to find a mistake. It's a real there is some invisible mistake. Number real, yes, it's okay, k, because it doesn't say about and 3.5 divided by 2 SIM. And did you define SIM?
Yeah, I did it. First of all, the error showed up, then later I did it.
So you know, you have it. Maybe you can check, compare your program with some. So did you succeed?
No, sir. I'm just trying.
Just try. It also doesn't work. Oh, excuse me, please, can you give us advice? Because, yes, oh, this is good. Because, can you compare the codes here and there? I cannot see any mistake. I cannot see. No, this should be connected. Some mistake. 1 minus q divided by 2. Q. Oh, really? Q square. Or maybe q square root of 3 divided by 2, right? Y minus q divided by 2. Let us check the following way. So you have some kind of a mistake which is invisible, yes? Oh, but maybe you see you have this very interesting triangle, right?
It's kind of rotating, right?
1/3, 1, 2, no, KK1,
आपकी कोई यहाँ use
One.
करते हो
So,
ऐसे करके देखता हूँ
so if you put here, uh, please print define interval, okay? So define interval, you know, unit interval, and then put it here instead of KK, and look what will happen. Yes, yes, you are perfect. You are perfect, and you too, I suppose. So did you? Oh, very strange. You have nice curve, but not of that sort. So let us wait for the result. Did you succeed? This is okay, but the second is not.
The second one is not running actually. I
Maybe,
tried it many times.
maybe I.
Writing the code again.
You're writing the code.
Because maybe there is some memory.
So maybe I made some mistake here on the blackboard. How do you think?
no, it's fine.
It's fine. But why it happens that one person does prints these letters and everything works, and the other person prints the same letters but nothing works? Of it. So did you?
The same problem I have. Same problem.
Yes. Yes. Computers are very sensitive. Yes. It depends on who. If one comes to this computer, it begins to work. Then if so, did you succeed? And did you try? Let me. But SIMQ. You need to print different. You have Q011, but here you have. So let me draw these letters in greater scale. So I will enlarge this picture. Maybe it was because I was writing the letters in some improper way. Minus Q 0 union. Here you have 1 minus Q divided by 2. 1 minus Q divided by 2 multiplied by square root of 3, right? And it is multiplied by Q. And all these things are in parentheses. And the second part of the union is SIM. Here you have Q 0, 1 minus Q divided by 2, Q square root of 3 divided by 2, all this closed, and then all these parentheses are closed, and it is multiplied by k. Yes, I write it in greater letters. What? It works? Almost works, but can you enlarge? There are two problems for me, not for you. One problem's very small letters, and second that they are very dark. Oh, sorry. Okay. Let us return back to editor. Yes. And let us compare what is 0.87?
Root 3 by 2.
Square root of 3 divided by 2. Just write it exactly. Because otherwise there will be a gap between points, you see. Just write square root of 3 divided by 2. Yes?
I want to understand, sir, that triangle, actually what you were trying to do actually, this triangle you made, no?
Yes?
Yeah, so what was the S1, S2, can you just...
S1, S2, S3, S4? So, I grouped, this is S1, 1 and Q. This is S2, this translation multiplied by this contraction, and this is S3, and this is S4. So, did I answer your question? Okay. So did you succeed? Oh, it's okay. This is wonderful. So, do you know how to find the dimension of this?
The vertices?
Of the attractor?
Okay, no sir.
Yes, it is very simple. Oh, sorry.
Okay.
It is here. Of course, you can solve an equation, but fortunately, this program finds dimensions very well. So, can you switch from dark theme to black and white and black? I don't know, but usually I have white screen and black letters. Yes. Oh, you need to. So you found the. And did you? So, did you succeed finally? Oh. And nobody can help you. So you both are in danger. You are okay. And you too. Oh, that's wonderful. So can we proceed? We need to make one more thing, and it needs some explanation. Because if you have an attractor if you have a dendrite, you need to find its main tree. So, at some moment we need to proceed to the next step. Yes? So, please raise your hand who cannot construct this figure. How many people didn't construct? 1, 2. Yes. So you have some mistake or yes. Q number real 0.1 number real, and what is the union sign? Delete this union sign. Okay. Error. Oh, one more error. So there may be Q. And what is Q3? Q multiplied by 3 to the power. You forgot the multiplication because the program considers as Q3 one more name. Again, you need to look carefully. And what is this? 2 point, what is it? Between 2 and this comma? Comma. Yes, comma, then please check. Can you enlarge this scale and return back? Okay, because I cannot. 1 minus Q. Sorry, 1 minus Q. What is 1 minus Q? I don't understand. Where is 1 minus Q? There is some strange expression on your. This is. Please compare what you printed and what is written in your. So you are okay?
Yes, I got it.
Yes. I'm very sorry, but I need to proceed to the next stage. Yes. Initially, I supposed to come with one of my former students and now colleague who could serve as assistant, but he was rejected the visa by some unknown reason. Yes. Yes. If we were two, then we might be able to check all mistakes, because checking mistakes is a very difficult task, as you understand. So our problem is to find. So if you have this attractor, you have the main tree, which goes something like that. You see? If you have a dendrite, then its vertices, there is a minimal subdendrite containing all its vertices, and it will be a tree, topological tree. And we need to find this main tree. We need to find this main tree equations. So we need to write these parts. So all these branches of the, since this case is symmetric, then we have a curve gamma, which consists of this part, this part, this and this part. And all this, and this is also the same curve gamma, rotated by some angle. So we can write the equation for this gamma. So let this curve be denoted by gamma. Gamma. Then we'll see that gamma is equal to one image of gamma, second image of gamma, and third image of gamma. Yes? So it will be, if this is S1, so gamma will be equal to S1 of gamma, right? Union the image of gamma under rotation by the angle 2 pi divided by 3 with respect to the center of this triangle. Yes? How to rotate a triangle by 120 degrees? You can rotate it if this point is 0. You need to rotate it 120 degrees and then to translate it by 1. Okay. So let be R. R will be a composition of translation by 1 and rotation by the angle 2 pi divided by 3. So it will be S1 of gamma union S1 multiplied by R multiplied by gamma. So it will be S1 multiplied by gamma union S1 multiplied by 1 by R of gamma. Yes, our union is drawn. And then you have, and this is S1, S2, S3, and this is S4. And union S4 at gamma. So if you write this equation, you will get this part of this curve. Yes. And suppose to make the whole main tree, then you will get 3. Tree will be equal to 1 R multiplied by R and multiplied by gamma. So this will give us the main tree of the dendrite. Did you understand how it was done? No? So we have the main tree. It consists of three symmetric curves. Right? So we denote this part of curve by gamma. Yes? And notice that this part of gamma is the image of gamma with respect to S4. And this part of gamma is the image of gamma with respect to S1 and with respect to S1 composed with rotation by 2 pi divided by 3. Yes? So we write it. we define the rotation by 2 pi divided by 3 this way. Yes? And write the tree is that gamma is S1 union S1 R gamma union S4 gamma. Yes? This equation will give us gamma. And this equation gives us the whole main tree of this right. Okay? Can you construct it? So Friday is 11:12, 12:01 is invited talk, 2 to 3 one more lecture and one more tutorial today. Okay, do you have questions? Yes. S4 is this. You see, it's not convenient to write this expression. Yes, for our use, we define S4 like this one. Oh, no. S4 is SIM, yes. No. S4 is, sorry, S4 is this map. This is a map which sends this triangle to central triangle. Yes? Did I answer your question? What? S1 is Q. S1 is Q. S2 is 1 minus Q0 multiplied by Q. S3 is equal to 1 minus Q divided by 2. 1 minus Q divided by 2 square root of 3 multiplied by Q. Multiplied means we print a star. So did you succeed? Oh, that's wonderful, and you found it. So you need to construct a composition of K and its main tree. Yes, it's perfect. Okay, so there are people. success? Oh, yes, yes. Oh, no, you have the dendrite, but not main tree. Okay. And did you find your mistakes? Oh, it's discontinuous. Discontinuous curves, it's very interesting. Can I... one minus... So, oh, no. It's discontinuous, the whole object is discontinuous, or this is a tree.
Yeah.
Because k is okay. No.
No, this G is okay. G, I think.
This is G. No, G is... No, G is... you mean which except? Or... Very interesting, yeah, this... This is from curve, this is I don't know what, but it is good. K11. This is all, yes, I understand what it is, and I don't understand what it is. G1 I 20 02 22 11 multiplied by G. Sorry, 1/3. It's okay. I 0 0 20 02 22 11 multiplied by G. It's a mystery. Everything is okay.
Where is the mistake, sir?
You know, to find a mistake, it is much more difficult. But it doesn't. Let me do once more. 1/3 multiply by I. Maybe it doesn't like I. Okay. Let us write 0 0 0 0. Maybe it's some kind of personal reply. Oh.
So it's not finished. That's what it is.
Well, 3 is 1. Yes. But you cannot apply it. I need to check this one. So can we comment it? Okay. I forgot how to comment. Okay. It's not good when everything is. So can you finish S3 and then I will check it. Yes. Okay. So main tree is yes. Oh yes. Fantastic. It's fantastic. Okay. And now it is 12, right? Friday? It's 12, we need to finish. Because at 12 I need to begin my talk for the faculty. I'm very sorry. But you can stay here and do what you like. Mic is turned on. Yes, okay. So, I am very thankful for the high auditorium for giving me a possibility to make this invited lecture, which is a great honor to me to share some of our results with all of you. So, my talk will be devoted to the topology of simply connected fractal squares. Really, these results can be applied not only to fractal squares, but also to Bedford-McMullen carpets and Baranski carpets. But it's more easy to show all these things on squares and then extend it to other matters. What is this fractal square? So, fractal square is very simple kind of fractals. It is constructing the following way. We take a square, say n multiplied by n. Yes? We take union square and divide it into n squared smaller parts. Yes? Then, after that, we choose some of these smaller squares and look at the lower left corner points of these squares. So, coordinates of these corner points will be di divided by n, where di are the part of a set D, and D is 0 n minus 1 squared. You see, each coordinate is KL, where KL divided by n, where K lies between 1 and n minus 1, and L lies also some integer number between 1 and n minus 1. Yes. And we construct a system of similarities, sending this large square to these distinguished squares, to these chosen squares. Yes? So we write K is equal to union of SI of K, but SI of K is a multiplication by 1/n and translation to the number di. Therefore, we can write it in more compact form. D plus K divided by n. Right? So, this is the definition of a fractal square. Very simple. So I need not remind to you the definition of a self-similar set because I repeated it several times. So this definition of fractal square is the following. So we have the set of digits, digit set D, which is a subset of 0, 1, and minus 1 squared. Yes, and a fractal square is the set which satisfies the equation K equals to K plus D divided by n. The immediate consequence of this equation, which explains why we call these points digits, is that each element of of this fractal square can be written in the form sigma, the sum of dn divided by, dk divided by n to the power of k. So the points of a fractal squares can be represented as infinite fractions, but the digits in these fractions are not 0, 1, 2, 3, 4, 5, 9, but the digits in these fractions are just these chosen points. So this is a fractal square. Very interesting and simple. So this is a typical fractal square, 5 by 5. So I have a square 5 by 1 by 1. I divide it into 25 parts, and I have chosen these parts. And after constructing the system of similarities, I get this fractal square. It is obvious that if this square if these copies, the intersection graph of the system of these copies is connected, then fractal square is a continuum. Yes, but the problem of how it is connected is very interesting, because each square has 1, 2, 3, 4, 5, 6, 7, 8 not neighbors. Because squares can have side neighbors and they can have vertex neighbors. And if a vertex belongs to fractal square, if a pair of opposite vertices belong to fractal square, then these two copies will have non-empty intersection. They will intersect in one point. From the other side, if two squares have common points on opposite sides, then the intersection will also be non-empty. Yes. Oh, this is a faculty coming. So a fractal square is a special case of so-called fractal cubes, and fractal cubes can be made in all kinds of dimensions, and there are two. One example of a fractal cube is very, very familiar to you. It's a Menger sponge. Yes, it is made of 20 cubes, smaller cubes, and this is some kind of variation of Menger sponge, because it consists of two groups of cubes. One is inside the other and they do not touch. Yes, therefore this fractal cube has uncountable number of connected components, uncountable family of connected components, and they are all, tied together. Like, so we have a kind of Menger sponge which is outside, we have a kind of cross, and we have also a great number of components which are in between them. And they form such a nested family of components. So the problem of connectedness of self-similar set is related to so-called self-similar boundary. So if you have a self-similar set, for example this one, you have a self-similar set, its copies intersect each other. Yes. So these intersections of copies form so-called critical set. Yes. But if we consider maybe a more complicated example, like this, we'll find very interesting property that this intersection points, if we take the preimages, they give some other points. And if take the preimages, we get other points. And the set of all preimages of intersection points form the set of addresses of preimages of intersection points form so-called post-critical set. If this post-critical set is finite, then we call the self-similar set post-critically finite. For example, Sierpinski gasket has these three critical points, and their preimages are this, and these 3 points are called the self-similar boundary of a self-similar set. Because all copies of self-similar set intersect by the images of the points from boundary. So everything which all aspects of relations between different copies of a self-similar set are expressed in terms of the points of self-similar boundary. If the self-similar boundary is empty, then the set is totally disconnected, yes? If a self-similar boundary consists of 3 points, the set is very simple. But of course we can construct a self-similar set which is a dendrite and which has infinite self-similar boundary. How to do this? We just need to choose proper points, because each point has a sequence of its predecessors. Yes? So a point has address I1, I2, I3, I4, etc. X is image of this sequence. And if I take this address, then Y is P of I2, I3, etc. Then X is equal as I1 of Y, right? So Y is the predecessor of X. And then if we begin to shift along this sequence further and further, we'll get this infinite sequence of predecessors. But in some cases, these predecessors are always the same. For example, this point has 2 predecessors, this one and this one. And these points are predecessors of themselves, yes, because these are periodic points. So this point is an image of this point and these 2. So the critical set is the set of points of pairwise intersection, and the set of all the predecessors of critical points form a self-similar boundary. And our interest is to understand how the self-similar boundary of a fractal square looks. As I already explained to you, if we have a self-similar set and its copies have non-empty intersection, then we can form an intersection graph. If this graph is connected, then the set is connected. But when we consider this intersection graph, these intersections may be very large. The other thing happens when the system has one-point intersection property. Then the intersection graph will look something like that. In this graph, we consider the points, intersection points, as the vertex of second kind, and we have more detailed intersection graph. So the attractor K of a system S is connected if the intersection graph is connected. And if a continuum possesses one-point intersection property, like in the case of Sierpinski graphic casket, then we can make a more detailed intersection graph with vertices of two kinds. Vertices of one kind are the copies, and the vertices of second kind are the intersection point. So if we have a self-similar set whose intersection graph is a tree, and it possesses one-point intersection property, then the attractor is a dendrite, and we built such dendrites. We already created such ones. So this theorem was proved quite long ago. Yes, first it appeared in the paper of Band as one line. If this system has such graph as a tree, then the attractor is a dendrite, without any explanations. But of course, it had to be considered in more detail. Now you see a fractal square. You see? Yes. And its attractor, it's a system, this is a system of squares, and this is the attractor, and this is the intersection graph of this system. Please look. What can you say about this intersection graph? It is a tree. It has no cycles. Therefore, this picture is a dendrite. It's a dendrite because it cannot have any closed loops inside. Of course, if the intersection graph of a self-similar square is a tree, then the attractor is a dendrite. But is it true to the other side? Because we can consider dendrites whose copies intersect in a line. Or, as I showed you in previous example, we can construct a dendrite whose copies intersect in some complicated topological tree or even a subdendrite. But this cannot happen for fractal squares, because if a fractal square if the intersection of two copies of a fractal square is simply connected, and it is not a point, it can contain an interval. But if it contains an interval, and this interval is also consists of smaller copies, but to have an intersection of two copies in one interval, we need to have one interval on one side, and the other interval will be on the other side. But if we have the intervals on two sides, then this picture will repeat in smaller copy which will lead us to appearance of loops, of closed curves, so it cannot be a dendrite. Therefore, we have very interesting theorem. If a fractal square is simply connected, then either it is a square, completely filled square, or it is a dendrite. There are nothing between these two possibilities. There are no intermediate possibilities. This statement is true not only for fractal squares, but also it is true for Bedford-McMullen carpets. And even some topological carpets are more complicated structure. So what happens with the components of a fractal square? So if you have a fractal square, then it has 4 sides. Yes, these sides may be empty, may be non-empty, but each side is an intersection of fractal square with this interval. And it is a fractal square itself because it is generated by those chosen squares which intersect this side. Therefore, each side of a fractal square is a fractal segment. So it is some kind of counter set. We take a segment, divide it into n part, choose some of these parts, and the attractor of this system will give us a fractal segment. The problem is, suppose we have 2 fractal segments, then their intersection can be written in this form. And so maybe I will skip these details. It depends if you have 2 fractal segments. Yes, I will write one segment and the other segment. Right, one segment will be marked by red lines, maybe this one, and the other segment will be marked by green lines. Say this, and this. Yes. So some of these parts will be common, yes, and some of these parts can intersect in n points. Yes. So if you have more than one common part, then the intersection will be a counter set. It will be uncountable. So if the number of common parts of 2 fractal segments is more than 1, then the intersection is uncountable, and we don't need it because we need one-point intersection property. The second problem is if we have only one common point or only one common copy. In that case, there will be a fixed point, and the intersection may be countable, or it may be 1 point, or it can be countable. If when it is countable, for example, consider this the case when say we have these copies and these copies, right? If red fractal segment contains this copy, then it contains this point. If a green fractal segment contains this copy, it contains this point. Therefore, this point will be common point of these two segments. Right? And it will repeat countable number of times. It will repeat countable number of times. Therefore, the intersection of two fractal segments contains one or less parts, then the intersection may be countable, but in some good cases it consists of only one point, and we are interested to have only one point intersection. And these common points of the intervals give rise to common points between copy. For example, if we have two squares here, yes, then if two copies meet on such side, then this point comes here, this point comes here, and that's all. What I have to do? Exit? No. Oh. Can I erase this insect? Yes. Yes. And for example, if we have two copies which have common vertical side, then they will meet in this common point. So if on each pair of sides we have only one pair of common points, then everything is okay. Our set will have one point intersection. So in that case, if we have if we have a fractal square like this, you see it has these two sides have three intersections. So there will be any two, if we take this fractal segment and take this fractal segment, they will have one and one and 2 points. And you see that on each vertical side, when they are neighbors on a vertical side, we have 2-point intersection between this copy. It is good just for us to know that such possibility exists, but to consider the simply connected case, this can be ruled out. This possibility needs to be ruled out. Yes. So, summing up all the problems, we see that if we have a simply connected fractal square, which is not a line segment, then it can have 4 types of boundaries. 4 types of boundary. First type of boundary, then we have 2 common points on opposite side, opposite vertical sides, and 2 common points on opposite horizontal sides. Yes, the second case, it's a boundary of a type 2 when we have 2 common points on vertical or horizontal side and have 2 common points on opposite diagonal points. Yes. Third one, if if a fractal square is simply connected, then it can have boundary, so similar boundary of this type, when we have two pairs of opposite diagonal points. And finally, it is possible that we have opposite diagonal points, opposite vertical points on vertical sides, and opposite points on some of diagonal. It will be type D. So the four boundary types, A, B, C, and D. But D can be quite simpler. We can have this point, and this point. These 2 points are opposite points on horizontal sides. These 2 points are opposite points on vertical sides, and these are diagonal points. So they're type D3 and D4. For example, this is a fractal square of the type A, because we have 2 opposite points here, and we have 2 opposite points there. So they intersect, the copies intersect on horizontal sides or on vertical sides. And this is a type B because the neighboring points lies on diagonals. So all this fractal square look this way. And it is impossible if n is even number. Only n must be odd. For example, this fractal square has the order 1, 2, 3, 4, 5, 6, 7. Yes, it's 7. It is a square of 7 by 7. And this is a type C. Type C. We have a vertical and diagonal. Type C is, I forgot to mention it. So it is possible when we have 2 neighbors on a diagonal and 2 neighbors on opposite vertical or horizontal sides. It's a type C because we have this vertical neighboring and we have diagonal neighboring. But how do you think, is it a dendrite or not? Do you see any cycle here? No, there is no cycle because intersection graph is this, and this. Yes, intersection graph is a tree. Therefore, this fractal square is dendrite. And this is a fractal square of the type D3. When 2 squares can intersect on a vertical line, 2 squares can intersect on a horizontal line, and also they can intersect on a diagonal. But only on one diagonal, because it is impossible to make more than one diagonal in that case. And this is D6 when vertical neighboring points are these 2. Yes, horizontal neighboring points are diagonal neighboring points. Horizontal neighboring points are these, and diagonal neighboring points is here. Yes. So it is type D6. So if you have a fractal square dendrite, then for any point, the order of this point cannot exceed 4. Because why it is so? If we take a fractal square and sum of its neighbors, if we have 5 neighbors, then we'll have a cycle. Because an order of the point is the number of neighboring component to a fractal, to a copy which consists. So there are several relations between copies which finally lead us to the following result. So fractal square dendrites may be divided into 7 types depending on the form of their main tree. So the main tree may be this way, it may be this way, this way, this way, and this way. If I had the time, I could explain it in more detail, but now we need to finish. So these are fractal squares of the first type, when the main tree is a Jordan arc. You see, this is a fractal square, this is a main tree. It's simply connected. Oh no, so it is just an arc. The second type, when the main tree has this form. You see? So one point, this common point may be on the boundary and even on the self-similar boundary, but there are 4 possible types of fractal square with such a main tree. Then we can have the third class. You see it? When main tree is diagonal cross. It can be of type A. Yes, it may be of type B, and it may be also of type C. And main tree can be this type. It can have 4 vertices, and 2 vertices are of the order 3. So these are examples of such main trees. And we can also construct the fractal squares with main tree of that configuration, and of that, and also of that, and finally we finish the talk and have a break. Thank you for your attention. And now,
So if you want to ask any question,
yes, I will be very.
you want to ask something? Yes, please.
Yes.
The theorem showed from this number of neighbors were taken as the order, right? Number of neighboring copies were taken as the order.
Yes. If we have a point of order 4, then there are 4 arcs issuing from this point. So if we take a very small neighborhood, then we'll see that this small copy will go to 4 neighbors. Therefore, we have 4 neighbors.
There will be a cycle.
No. This picture is, it belongs to different case. So if you have a point, yes, and you have 4 arcs, yes, 4 arcs. Each arcs correspond to some neighbor of this copy. It may be this way, or it may be that way, or maybe some other way. But if we have a point of order 4, then we have 4 copies defining this order. Because if you have 3 neighbors, we cannot get 4 arcs. Each arc goes to separate neighbor. You know, the intersection with each neighbor is 1 point. If you have 2 arcs coming to the other neighbor, then we'll have 2-point intersection, and it cannot be dendrite. It will have loops. So are there more questions? So the only question is when we finish. We finished just now. Thank you for your attention.
If there is no question, let us thank the speakers.
And I also applause to the auditorium who took pains to hear all that. Yes. Yes? Yes. Okay, it works. But I won't use this picture, it's just an enumeration of possible tree types. And now we need to make some, learn how to solve some problems. Yes, because the problem is how to construct an equation of the main tree of self-similar dendrite. And this is a dendrite called Hata tree. It appeared in the paper. There were two Hata trees, and this one appeared in the paper of Masayoshi Hata in, I remember, 1985. It's quite old. So the problem is to construct this dendrite, and second, to find its main tree. So first problem is what is the self-similar boundary of this dendrite? So there is one intersection point, just one. But if you consider its pre-images, then you will see that this point is a pre-image of this point is the pre-image of this point, this point and these points are also pre-images of this point, so the main tree will be something like that. I don't know how it looks. Okay, so we can only imagine how it looks like. But first of all, we need to find the parameters for such trapezoid so that the union of its two copies would intersect in this point. Can you find the parameters? Not very easy. So we suppose that it is, say, 1, 0, 1, and then we suppose that this is angle is alpha. I'm not sure that every alpha will fit. So what it will be? Can we write an equation for this trapezoid? How do you think? Can you compute the parameters under which this trapezoid intersects in this point? It is not very complex, I think. To tell the truth, maybe I will skip this problem because it will take some time to find these parameters. Therefore, Excuse me, please. This problem is not that simple. I just remembered it. So consider we took a Vichik set and we can make a deformation of a Vichik set. Do you understand this? Yes. So the problem will be to find first to find the. So we have some kind of angle alpha. We also have this coefficient Q. Yes, then this coefficient is easy to find, and after that we can find these lines. They are the same. Again, there is a symmetry, so these lines will be symmetric. So there will be two parameters of which this fractal set depends. It depends on Q and alpha because these points are defined by these parameters, and after that all the other points. One very important theorem. Suppose we have a regular polygon with the side 1 and which has n sides. How to write the rotation of this polygon, which toggles its vertices? This to this, this to this, this to this, this to this, this to this. So it will be a rotation in the angle 2 pi divided by n, yes? But this point is not 0, so it will be, it can be expressed in the following way. First, we rotate it to 2 pi divided by n, then we get this polygon and translate it by 1. So this rotation of this polygon can be written in the following way. We have rotation in 2 pi divided by n and translation by 1. It's just in case, because we need to rotate the square, but the formula is good for any regular polygon with n sides, provided the sides are equal to 1. Okay, so now we have this picture. Yes, we can define this map. After that, we can rotate this map to these 4 points, and also we need to define this map. But to define this map, we need to understand what are the coordinates of these points. What are the coordinates of this point? If it is Q, this is also Q. Can you tell me what is the coordinate of this point? So it's a Q, it's Q cosine alpha, and this is a Q sine alpha. So Q multiplied by cosine alpha plus sine alpha. This will be the first coordinate, and the second, you see what it is. Q multiplied by so minus sine alpha, this one, yes. This is cosine alpha and this is sine alpha. So Q multiplied by cosine alpha minus sine alpha. If alpha is rotated by in a so am I right? Q cosine alpha plus sine alpha, yes. And this is Q cosine, and this is Q. The coordinate is Q cosine alpha minus sine alpha. Okay, so I just checked. So having these coordinates, it's easy to construct this picture. I switched it off. Yes, because it shrinks the screen and I cannot see anything in my. I will switch it on again. you saw some pictures, right? Oh, they are still here. Still here. There are 5 versions of an option. So these problems will be distributed at the end of today, and you have to prepare them till tomorrow. So if you wish, we can take one option and make a solution of it. How do you think? Will it be good? And 4 options will be distributed between you. Because we need to have an exam, and this will be a nice, very nice exam. Okay. So look at the first problem. So construct such a zipper. Are you able to do this? How to construct such a zipper? Construct a zipper and find its dimension. I think you can easily find it. So is it visible? Are you able to do? Let us check. Let us check your ability to make this assignment. Yes, you see. So first, construct the zipper. You see. So we have a polygonal line, and you need to construct a zipper. Construct the attractor of a zipper, but if you look attentively, you can say what is the dimension. So you need just to write down these mappings, yes, and then implement it in IFS style. And you can think that this is 1 and this is 1/3 if you wish. But if you wish a more complicated version, then you can make these sizes different. A, B, 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 A. And you can choose the sizes of the sides, and you think it's not interesting? How do you think? Is it good? Not very complicated, but not very simple, yes? I think there must be a kind of golden middle I don't know where to choose, to build, to construct, or to plot. You are better expert in English because you use it every day. So which? Build, construct, or plot? What word is better? Construct. Thank you. You helped me. And here we'll also, I need to do you have any questions?
Sir, what are the length we choose, like previously you were saying? Can you tell us?
There are two options. First option is 1, 1, 1, 1, 1.
Yeah.
It's very good.
Yeah.
Yes. I switched the generator of random numbers and found a random sequence 1, 1, 1, 1.
Yes.
Okay. And the other option is A, B, 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 A.
Okay.
In that case, you have a great variety of parameters to You need some assistance? You got the result?
No, it's not coming. This one.
Oh, you don't need this. Of course, 1 1 1 1 0 1 0 1 0 1 1 1 1 2 1. And yes, but if you have, you see, in this case, all these maps are not contractions, because they send unit interval to unit interval, yes? And the program will block all your efforts. It protests because it uses only contraction maps. So if you write 1/3 in front of this operator, then it will be okay. So if you have here 1 0 and 1 and here 1/3 1/3 1/3 1/3, then it will be okay. Yes. The other way needs computation. If you have say A, B, 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 A, then you will have you have two possibilities. First, you consider the case when 2A plus B equals 1, right? And you can use SIM. In that case, everything will. The other way, if you just consider these similarities, you have this contraction ratio will be A divided by 2A plus B, and this contraction ratio will be B divided by 2A plus B. So without some additional calculations, you won't have success. So in the case when you have 2A plus B equals 1, it's very good. Then you have, it will be 0, this will be 1, this will be A, this will be A, and this will be 1 minus 2A. And you have you can change the parameter A, but B cannot be independent. You have only one parameter. Yes, yes. Sorry. This is good, and you can absolutely, very good. So whatever you like, you can change the parameters, or you can make this way, A and B, right? Okay, and change A, and it will transform. What? It's okay.
Changing to the random ones.
Yeah.
A and B.
A and B, but you have A and 1 minus 2A. B is 1 minus 2A, but in that case,
I have taken A from 0.1 to 0.4. Is it okay?
A is taken from
0.1 to 0.4.
0. Even 45 will be 0. But not 0.5 is also good because you will get the interval. What?
Fractal square.
What? You constructed it?
Yeah, how to do that?
How to do this? You have this fractal square is 4 by 4, right? So you have numbers 0, 0, 1, 0, 2, 0. You see, I was not very careful and I didn't explain very well what is the equation of a fractal square. So fractal square has an equation k equals d plus k divided by n, where n is the number of sides. Yes, and d is the family of coordinates of these vertices. Yes, of these corner points. Yes, this is the D. What is the D in this case? So this is 0, 0, 1, 0, 2, 0, right? Then 0, 1, 2, 1, 3, 1. Then 0, 0, 2, 1, 2. And finally it will be 1, 3. Yes. How to write it in a program? I will show you it on some other example. For example, let us have a fractal square of this side 1/3 and which consists of these 5 squares, right? You see. So D will be 0, 0, 0, 0. I will write it in square brackets. Then it will be 1, 0, 1, 0. Then it will be 2, 0, 2, 0. Then it will be 1, 1, 1, 1, 1, 1, and this will be 1, 2, 1, 2, 1, 2. So this is D. You can just write it this way, D. So this combination of translations can be denoted by D in your FractTracer program. And then you write K is equal to 1/3 combined with D and with K. This is all. What?
Then k is equal to d plus k by n. What is that?
Sorry.
You have written d plus k by n.
D plus k by n, it was a definition of a fractal square, but if I process to the IFS style program, yes, I replace D by a composition of translations. These are translations, yes. I take the composition union of translations, yes, and apply it to K, and then divide it by n. So this operation is just written in this form, but this is the same. So there is a Telegram group for discussion of fractal or IF style. Sorry, IF style fractracer. It was my dream to make something with fractracer, but I couldn't. So you can join this group and discuss different things. Yes. Do you see it? Yes. This group, it is not, is it visible here? Yes. Oh, here it is. There is a link. Very complicated link. I will write it. Link is, don't miss any letters. Yes. Okay. So all the news are here. This is, oh, this is good. Yes, and you change the parameter. What?
This is the D, means KC, you have written there, K equal to 1 by 3 star P star P.
So D here, so you mean what is this D? What you? So when you finish this second, and then there will be third assignment to construct such a fractal composed of triangles. It is very simple. So when you manage with these three problems, I will continue to explain the open set condition because I didn't finish it in the morning, and maybe I will.
This square, can you just scroll down? I think
Yes. Oh, is it okay? Yes, it is. You need to put the battery.
Oh, battery is working.
Working. Yes.
Now speak.
One.
Okay, now okay.
Oh,
Okay.
yes.
Yes.
But lamp doesn't show itself. Yes. Okay. So did you make it?
Yes, sir.
Wow, fantastic. Very good. So if everyone has made it, then we'll proceed to some other things. Tea break in 10 minutes. 3 p.m. 1 second. I need to consult. 3 to 3:30. Oh. Yes. It's okay. Please. No problem. Just switch off the camera and we'll find the connect relation between A, B, and alpha. So they have done everything. After that, so you just keep this things safe. Thank you. Okay, so can you write the equations? So if you have this alpha, this is also alpha, but this will be what it is? It is pi minus 2 alpha, right? Pi minus 2 alpha. So a squared multiplied by cosine pi minus 2 alpha is b. Yes, a squared multiplied by cosine pi minus 2 alpha is b divided by 2. Right. Then what else? 2a squared plus 2ab multiplied by sine alpha will be 1. Yes? So these equations are sufficient for us, yes? I don't know in which terms it's better to express the parameter in terms of alpha. Most probably in terms of alpha, yes? Alpha. Let me check. A squared plus AB cosine alpha is 1/2. 1/2. And then 2a squared multiplied by cosine, this is alpha, this is alpha, right? So cosine pi minus 2 alpha equals b. Oh, so we can eliminate b. We can eliminate b. Then we'll have alpha squared plus 2a cube cosine alpha cosine pi minus 2 alpha minus 2 alpha is 1/2. 1/2. And cosine pi minus 2 alpha is minus cosine 2 alpha, yes? Right? Alpha? Pi minus alpha. So it is minus 2 alpha cube cosine 2 alpha. So it's not easy. It's better to choose some value. If you find some Yes, not very easy to find these numbers, or you found. You have question? Tell me. Or I have some mistake, no?
0, it is a square, a square is comma 0.
Yes,
When it's 1, comma
yes,
0, it will be minus 1 minus a square comma 0.
right.
Sin alpha.
Mm-hmm.
It will form a triangle. Sin
Yes,
A alpha. We will get a perpendicular and with respect to this, and it will be a cos alpha a sin alpha at this point, and this length is b. That means it will be a cos alpha plus beta plus b comma a sin alpha this point,
yes, yes,
and rest is this point. We can form a triangle here,
right.
and we have this is midpoint is one half,
Uh-huh.
and we have
Some relation between A and B?
we have this length, total length,
Yes,
a sin alpha
yes, yeah.
minus this length we can find this is a square sin, as this is angle is pi,
Mm-hmm.
it will be pi minus alpha, and it is midpoint, because
Yes.
of pi minus alpha by 2 this angle,
Mm-hmm.
and sin of pi minus alpha by 2 into a square will be a, and this minus this point is
Yes,
we have all the parts parameters.
but you see there are two equations, yes? So everything depends only on one parameter.
Yeah, everything is depend upon a for now.
You expressed everything in
It is in a, it is in a, it is in a, everything is.
everything
A is
depends on
midpoint.
A.
A, and here only this, in this case we have used beta, B there, this point. Or rest all is open A and alpha.
No, B is also expressed in terms of A.
Okay.
B is expressed in terms of A, and alpha is also. Everything depends on
As
one.
we can find it, it is a square, and we have to find this value. Then
Mm.
we can verify this.
If you make this right angle, then it will be
It
good.
will be basically square or rectangle. Let
Oh
me
no, you cannot make a right angle here because this.
obviously this will be anything anywhere else. This point will
Mm-hmm,
be somewhere else. We can see.
mm-hmm, mm-hmm. Yes, I don't know how to solve these equations. I forgot because I made it, but now I forgot how to solve them. Okay. Okay, so you finished the job, yes? So I don't remember how to find the parameters for this. Or maybe we can just or maybe alpha let alpha be 2 pi divided pi divided by 3. No? What angle is it good?
I have removed that b.
Yes?
I have removed that b. This large triangle, there will be alpha, and
Yes?
this length will be
Yes.
hypotenuse into cos alpha,
Yes,
and
yes.
1 minus that much will be b is
Okay.
removed.
Okay, so please construct it. So if you manage the parameters, then construct it.
So I have to just what we have to do? Have we have to just translate, or
So
what we have to do?
so there are two maps. Let me check because I had this Hatta double somewhere in my records, and it will be more easy to find it. I cannot remember. Hatta double. Maybe it is here. Oh, I have it, yes. I have it. This double. Okay. Do you see the picture? Rendering. Background. View palette. Okay. Okay, see. So now it's visible, right? I did it long ago. You see, it is possible to construct it, but I don't remember how to make this. Hot double, d0, di, main tree. Oh, we have. You see? But I forgot how to construct a formula. Maybe I will find it. Oh, where is editor? I look to editor and source. Hey. Oh, it is a problem to find it. Okay. At that moment, I cannot remember how I computed these numbers, but they are in the program, and I will look at it and then explain. I wish you to make one more experiment. One more experiment, and then we'll proceed to other things. Take the equilateral triangle. Yes. Make here two smaller triangles, and make here two such triangles. You see? So we'll make a self-affine dendrite. So this map will send. Oh, let us excuse me. Let us make it the following way. I take a equilateral triangle and make these two copies less than one half. So it will be some number, maybe 0.4. Then I have 0.6, yes, and I add two affine mappings. These affine mappings will send this triangle to this one. And this affine mapping will send this triangle to this one. Okay. This vertex is preserved. So let us look what happens if we construct a self-affine system. So if it's 0.4, this will be 0.6, this will be 0.6. Yes. Since this system is symmetric, we can use the symmetry with respect to this bisector. Yes. So we just write these two maps and then make a reflection with respect to line which goes at the 30 degrees angle. Okay, so but we need to have this triangle, these two triangles, they must be, this height of this triangle will be such that it doesn't touch this this bisector. Okay. So what we have to do? We have two maps. This map will be 0.4. This map will be 0.4. First, it will be translation by 0.60 multiplied by contraction with the ratio of 0.4, right? And this map, so you need this parameter h, it must be, so h divided by 0.3 must be less than this. This is 1 divided by square root of 3, right? Because the tangent of pi divided by 6 is 1 divided by square root of 3, right? So h is less than 0.3 divided by square root of 3. So if you take this h and now you construct a map which sends this triangle to this triangle. So it will, the y-axis has a contraction h divided by 2h divided by square root of 3. Yes, and the x-axis has the contraction 0.6. Therefore, this map will be written in the form S1 of S1 will be equal to matrix 0.6, 0, 0, and the value of 2h divided by square root of 3. Yes? So you need to compute this h. Compute this h so that, and S2 will be more, have more humane form. It will be 0.60 multiplied by 0.4. Yes, but we have not 2 maps, but we have 4 maps. So we need to have a reflection with respect to this diagonal. Yes. Maybe it is better to do in slightly different manner. Okay. So how to reflect? How to write a reflection? So we have a line with which which has angle A with x-axis, yes? And what is the reflection with respect to this line? How to draw a reflection with respect to this line? So if you have a point xy, yes? You have a point xy, it is reflected to this point. For example, xy are cosinus alpha, cosine phi r sine phi, it goes to, and this is alpha, this will be r. So if you, this is r e to the power of phi, if this angle is phi, then this angle will be, you have alpha and phi, and this angle is alpha minus phi, right? This angle is also alpha minus phi, so you take this angle will be 2 alpha minus phi, 2 alpha minus phi. Right? So if you have r cosine phi r sine phi, it goes to r cosine alpha minus phi 2 alpha minus phi r sine 2 alpha minus phi. Yes, these computations are too not convenient for us, so let us make the example more simple. We take a right triangle. You have two such maps, and you also have two maps which send this triangle, for example, to such one. You have a map which sends this triangle to this one, and then you have a reflection in this diagonal. So can we write this map? Sorry, I am a little exhausted and my examples are not good. My examples are not good. And what? Yes, I have a, tuition till 5:30. It's okay. So let me continue talking about open set condition, which I didn't finish in the morning, and now we can explain it. Using my notes. So suppose the system S satisfies the open set condition, and we considered that index space or address space, and we so we have the system S, S1, Sm, and the coefficients are Q1, Qm. So we found the similarity dimension, which is the solution of this equation, yes? And for this similarity dimension, we introduced a natural measure on I infinity, which is defined by an equation mu of I1, Im, I infinity is equal to Qi1 Im n to the power of s. So this was a natural probability measure on I infinity, which sums up to 1, so it is probability measure. And now we consider the measure mu weight on K, such that mu waved of A is equal to mu of pi minus 1 of A. So it will be the projection of the measure mu. So we have the space I infinity. We have a projection of I infinity to K. Yes. Here you have the measure mu. Yes, which is natural, and its projection will be mu waved. It is also called the natural measure on Q. Natural measure on Q. Let V, let O be the open set. Pen set. Of course, we take this open set is bounded. So we have union of Si of O belongs to O. Yes, and if we take closure, it is the same. And therefore, K is a subset of the closure of O. So if we take this open set, then the attractor will be contained in the closure of the open set. Consider the family. Oh, no. Take some ball BR contained in K. So we consider just the intersection of this ball. Yes? Some ball BR. So we can consider K as the whole space, but no, let us take some ball BR such that BR intersection on K is not empty. Yes. So we have a self-similar set, and for this self-similar set we take a point and take a ball and consider the portion of a this self-similar set which is contained in this ball. We'll evaluate. It's fantastic. Yes, we'll evaluate this natural measure of BR. We'll evaluate the natural measure of BR. How can we do this? We'll do the following thing, which was initially performed in Hutchinson's paper, and then it was a standard way of considering this problem. So we take a ball BR, and consider all copies of K which intersect BR and at the same time have approximately the same size as BR. So inside K we consider only those copies which are whose diameter is less than BR or maybe less than BR, but not very much. As I remember, so I will consider such family. Let QR be the family of such tuples or multi-indices. So each multi-index is I1, Ik for some K, and they are formed in such way that Qi1 Ik is less or equal than R, and Qi1 Ik minus 1 is greater than R. So we consider the set, we can think that the diameter of K is 1. So not to make our computations more complex, yes, we think that diameter of K is 1. We can do this just applying some similarity to the whole space so that our attractor is good. So what will be QR? So we have this ball and we consider the copies whose diameter is smaller than diameter of the ball, but the previous copies for them are greater than this ball, yes? So the immediate consequence of this inequality will be the following, that R is greater or equal than Qi1 Ik, and at the same time Qi1ik will be greater than R multiplied by Q minimal. You see what I have done? I multiplied this by Qik, then I have this if I multiplied this by Qik, then R is multiplied by Qik, but R multiplied by Qik is greater than RQ minimal. Okay. And I will write this inequality here because I will use it. You see that R is greater than Qi1ik, and more than RQ minimal. This family QR, we already discussed this family, yes? Because all the elements of QR are incomparable, yes? And if we take the union, if we take all Si of O, if I take such Si of O that belongs to QR, then this set will not intersect each other, yes? Because if we have an open set, and if we have two incomparable multi-indices, then the images of respective similar set with respect to these similarities will not intersect each other. First, do not intersect. But at the same time, this family is full in the sense that the union of Si of O closed, where I is in QR contains K. The images of the closure of the open set will cover the whole K, right? Do you remember, I already told something about that. You see, for any point in K, there is at least one multi-index, I1, Ik, such that this point is contained in a copy with this multi-index, yes? So, therefore, but each copy, but Si1 Ik of K is contained in Si1 Ik of the closure of O, because K is contained in the closure of O. Therefore, this union contains the whole K. Very good family, because it consists of the images of O, which cover the whole K, and they are approximately of the same size, and their interiors do not intersect each other. So we had very strange self-similar set. Its copy could intersect and so act themselves in very different ways. But when we take this open set condition, it makes them conduct uniformly. Conduct uniformly. So this is what we have done. But let us return to the ball BR, for whose measure we're supposed to evaluate. We have the ball BR, yes? And all these multi-indices were arranged in such a way that the images of K, the sizes of the images of K under these maps are commensurable with the, are approximately the same size as this ball BR. Therefore, in the set QR, we will take a special subset. So I don't remember what notation I used. It will be Q1. Let Q1 be the set of such multi-indices in QR such that SI of the closure of O intersects BR. Now we have the following picture. Instead of copies, we have the images of open set. The copies can intersect each other, right? But open sets are disjoint in the family QR. So we have the ball BR, and we have these copies corresponding to the family Q1. They are of approximately the same size as BR, yes, and all they intersect BR, but at the same time their interiors do not intersect. And if you have a family of approximately equal open sets which do not intersect, and we take some larger ball, then the number of this set can be evaluated, yes, because they are of the same size, do not intersect, and their volumes add up to the volume of the ball B. But we don't need very exact evaluation, we just need some number, because we're supposed to use the mass distribution principle. We need some constant. In mass distribution principle, we write mu of A or mu of BR less than CR to the power of S. No matter how great is the constant, it was enough to have some constant, yes? If we have some constant, then we are done. Okay. So, can you see this part of the blackboard? It was in a sleep mode. I don't know. Do you need this part which is written? Can I erase it? So, everyone allows me to erase it. Okay. The open set O is bounded, yes? So if we have a bounded open set, then and take some point in it, then we can draw a ball in which the open set is contained, and this ball will have radius r2, yes? And also for this point we can draw a ball which is contained in this open set, and it will have radius r1. Or maybe a2 and a1, because r is used. And this is the open set O. Now we consider these open sets which are arranged around this BR. We have a family of open sets who are friendly to each other and do not intersect. They do not intersect. You see, each of this set is contained in a ball, like that, and each of them contains a small ball, like that. Yes, and the diameters of these balls can be evaluated. So how to evaluate the diameters of these balls? This set is Si1 In of O. And Si1 In of O has the coefficient Qi1 In. And Qi1 In satisfies this inequality. You see this inequality? It is less than R and more than R multiplied by Q minimal. Okay. So diameter of Si1 In of O, I1 of O, Si1 In of O is contained in a ball. Si1 In of, you see, we took this open set, we took a point in it, and we have drawn two balls. One of radius r2 and the other was of radius r1, yes? So it will be maybe, I will call it B2 and B1. If you want object, I will call this by these two nice names. Yes, so Si1 In of O is contained in Si1 of In of B2. B2. And the diameter of Si1 In of B2 will be less or equal to Qi1 In multiplied by 2R2, yes? Qi1, but Qi1 In is less or equal than R. So it will be less than, or it is not R2, it's A2, because I know that I could have some inconvenience using R. So it will be Qi1 In multiplied by 2A2, and it will be less or equal than 2RA2. Okay, so all these balls have the size, have the radius less than RA2. So we have a picture. You have a large ball, and here are balls, and their size is 2RA2. 2RA2. And this diameter, 2RA2, and this radius is R. So all this picture is contained in the large ball, very large ball, which has the radius R multiplied by 1 plus 2A2. A2. So these are the large balls containing these sets S, I1, IN of all which intersect this ball. But for each ball there is an open set which also intersects R, and it contains a small ball. Yes? And the radius of this ball will be greater or equal than RQ minimal multiplied by A1. RQ minimal multiplied by L1. So this radii will be greater of greater or equal than R Q minimal multiplied by A1. So now we need to count how many balls of this radius can be contained in a large ball of this radius. It will be R multiplied by 1 plus 2A2 divided by R multiplied by Q minimal multiplied by A1, and all this will be to the power of n when n is the dimension of the space. Yes? Because a circle, if we divide the circle to disk areas of the disk, then we have squares. If we have balls in 3 dimensions, we have cubes. In an n-dimensional space, we need to obey the laws of n-dimensional space, but R about which we had our concern. We were concerned with the ball of radius R. By some happy coincidence, this R is cancelled. So this evaluation doesn't depend on R. So whatever ball we take, and if we consider the neighbors of this ball, yes, neighbors of this ball, the number of neighbors will be always less than this number, and it will be C. Therefore, the measure of this ball is the measure of its intersection with the copies. The copies which contained in these closed sets. And the measure of each copy will be I1 IN multiplied to the power of S. Right? I1 IN to the power of S. But I1 IN is less or equal than R. So the measure of each copy will be less or equal than R to the power of S. Therefore, we have that measure of BR is less than equal than C multiplied by R to the power of S. We are done. We are done. Yes. We can apply it mass distribution principle. And from mass distribution principle, it follows that house of dimension of K is greater or equal than S. But at our first stage, we proved the opposite inequality. Therefore, it is exactly equal to S. So, and this house of dimension is equal to box dimension and to similarity dimension, because similarity dimension is S. So now we finished this theorem, and we can make some. We have 1 more hour, but maybe we'll make a 5 minutes break at least. So this proof is very basic. What do we say? And it looks nice. If to pronounce it slowly. But if to pronounce it in fast words, it looks ugly. But what is interesting, from this open set condition, we also have one very interesting consequence, that each copy has a finite number of neighbors which can intersect it. So, if we take some ball, then the number of copies which can intersect this ball is, it depends on the radius of the ball, yes, and it is bounded, no matter how far we go. So this is very good regularity property. For example, if we have a self-similar dendrite which satisfies open set condition in space of any dimension, this dendrite can have only finite number of branches. It cannot be infinitely ramified, because each branch corresponds to some copy, and the number of copies is bounded from above. made of such a polygon. And inside this polygon we have one copy, second copy, third copy, fourth copy, and also we have 1, 2, 3, 4, 5, 6, 7, 11 copies. But due to the organization of this copy, this dendrite, this point has an order 3 because there are 3 branches. If we delete this point, these 3 branches split apart. Yes. So at this point we have 33 branches. The unification order of this point is 33. I will enlarge this picture. Sorry, let me picture. So we have a point of order 33 because there are 33 branches. This angle is 30 degrees. I cannot make 12 angles. They will glue together. But here we have 33 connected components if we delete this central point. And this is the main, main tree is, yes, this is, main tree is here. The main tree is very simple. This R, 3 R, 1 R goes to this point, 1 R goes to this, and not to this. But if we make a first image of the main tree, then we'll get this picture. And if we make a second iteration, then we'll find. Do you see this picture? Is it visible? Oh, yes, it is visible. Oh, quite well.
Please near the mic. Voice is not recording.
What?
Please near the mic.
Oh, yes. Okay, so we proved the open send condition, and now we can proceed further to some other things. So in case when open set condition is satisfied, the Hausdorff dimension can be found easily. It is just the similarity dimension, yes? But we can imagine this case when when the similarity, when the open set condition is not satisfied, but nevertheless we can find the Hausdorff dimension of the set. For example, consider this the following triangle. I will draw you one triangle. So let Q be at the golden mean. So Q squared plus Q equals 1. And I take the following thing. Yes, I will take, this will be Q, this will be Q, and this will be Q squared, right? So this copy will intersect. It is easy to construct this golden triangle, yes? And if you look at it, then since this is a Q, and this is also Q, then 2Q plus 2Q minus 1, Q minus 1. You see 1 minus Q, Q squared is equals 1 minus Q, right? Therefore, 2Q minus 1 is equal to Q minus 1 minus Q, right? It means that it is Q minus 1 minus Q minus Q squared, but Q minus Q squared is Q cubed, right? So it is, if it is K, if the whole triangle is K, this will be K1, this will be K2, this will be K3, say, and this will be K, K1, 2, 2, and at the same time it will be K2, 1, 1. Do you know the golden mean? It's square root of 5 minus 1 divided by 2, right? Okay. So you write Q equal to square root of 5 minus 1 divided by 2. Can you be so kind to build this fractal? Please. Please. Show your kindness. Okay. It's easy. Very easy. So there are only 3 copies. This number can be calculated because IFS tau can make such algebraic calculations. So with I think 15 digits after the comma. It's sufficient to make the mistakes invisible. They are very, very small. Okay, so can you do me a favor and construct this fractal? It looks very nice. Thank you. Do you understand what kind of maps this is? So first you need to define this Q. Then you made Q squared, then you have a translation by 1 minus Q. It is translation by Q squared too, right? 1 minus Q is Q squared. And so you have Q multiplied by K, and you also have Q multiplied by K translated by Q squared. And also you have Q multiplied by Q squared translated by Q divided by 2 and by X, and Q square root of 3 divided by 2 by Y. Okay? So there will be 3 maps, S1, S2, and S3. Yes?
In second last, how Q3 can?
K3?
Q3, Q.
What?
Second last.
Q cube. This is the intersection. The intersection is a copy of order 3. Yes. And when it is constructed, it is very well visible. Okay? Can you build this one? Oh, but this will be q squared. Of course, this is good that you have such an overlap, but let it be q squared. So maybe, oh yes, q squared. This translation is I made the wrong translation, yes? The The coordinate of this point, what it is, the coordinate? This is q, yes? And this point is q square root of 3 divided by 2, right?
Yes, sir.
Yes? Oh, no. Q square root of 3 divided by 2, it's vertical.
Yeah.
And
And Q.
q by 2 and q square root of 3 divided by 2. This is that point, yes?
Yeah.
So this operator will be q by 2 q square root of 3 divided by 2 multiplied by q squared.
Yes.
Yes, okay? And in this case, we'll have an equilateral triangle, but if we change the coefficient, it will grow higher. Yes. This is a very nice picture. But I constructed it something maybe in 203 or 204, and I cannot recover it. So I have just an image. I don't know how it was obtained. If you succeed in building it, I will be very happy because I have on the GPG, I have only GPG file, yes. Because when Dmitry Mikhontsev made the IFS style, then all PNG images which are saved by this IFS style program contain the IFS style code. It's very good. this is not the one. And this is a self-similar three-dimensional tile. Usually tiles are balls, but this tile is torus. This torus is composed of smaller copies of this torus. It was invented, so this IFS tile has the search machine. And Mikhontsev was always searching different fractals, especially tiles. So he's a person who has seen more fractals in his life than anyone else, because he saw thousands of them. Yes, and among them he found such unique examples that different figures can tile the space, but to tile the space with tori and also so we have this figure, yes, and then we add the same figure, yes, of the same size. Then we add one more figure and one more figure of the same size, and one more and one more, one more, one more. So did you make this golden triangle? Because I need to see your results, and then I will explain how to find its dimension. Because this golden triangle doesn't satisfy open set condition because it's his two copies of first order intersect in a copy of third order, yes? But it's an exact overlap, yes? Therefore, we can write, so measure of its, you say, q to the power of s plus q to the power of s plus q to the power of 2s and minus q to the power of 3s should be 1. And this will be the equation for the similarity dimension, which takes into account the exact overlap. So if you may take some program, mathematical, which solves such equations, cubic equations, yes, you will find S, right? You will find this, and then you can compare this S with the dimension which you obtain in your program.
But how can we mathematically say it's the dimension will be same? Similarity, basically S will be the dimension.
It's just counting of measure. Measure of this set plus measure of this set plus measure of this set will be measure of this set plus measure of this set. So I add two measures, three measures, and then I subtract this one. And all this will give us 1. So it's quite simple. Yes. So very good equation if you have Wolfram Mathematica or some Maple or whatever like MATLAB, you can find the solution, take logarithm with respect to q and get the same result which is shown here in But if you wish, you can also, this is not good, this is not a dendrite, but we can make a dendrite with overlap, yes? You see, if I take a cube and take copies in this cube, this will be 1, 3, 4, I must count these numbers. So it is, if it is q squared, it will be good. Q plus 2q squared, q squared is equal to 1 plus q squared. 1 plus q squared. Q plus 2q squared is 1 plus 2q squared. Not, I don't remember. We need to find some other number. Q. If I take this will be q, this will be q, then this will be q cubed. Okay, q cubed. Q. I don't remember, so, but we have such a dendrite which has an exact overlap. No, we need not make it. So if it is A and this is B, and this is B, then it should be, or maybe we can make it a different way. To make computation more easy, we can make it the following way. Oh no, we cannot do this way. I don't remember how to make it a dendrite. Of course, there is a way to make a dendrite this following way. Yes, if we make here one triangle and one triangle here, then it will be okay. Yes, so it is q. This is q squared divided by 2, this is q squared divided by 2, and this is also q, and this is q cubed. Okay, then we'll have a dendrite with overlaps, but also we can make dendrites with overlaps with cubes. So did you finish? Yes? Yes, okay. Yes, you're right. We have 10 minutes left. Yes?
So how we are writing its ratio is 2q minus 1.
Oh, I wrote the computation. Please, I will repeat it. It's very simple. So, you see, 2q minus 1 is equal to q minus 1 minus q, right? So it is equal to q minus q squared, right? So it's q multiplied by 1 minus q, but 1 minus q is q squared.
Why why we are taking 2q minus 1?
What?
Why we are taking 2q minus 1?
Why we are taking 2q minus 1?
2q minus 1. You see, this is q, and this is also q. So the overlap is 2q minus 1. You have 2q, but they are on the interval of the length 1. So their overlap will be 2q minus 1. Yes. So this golden mean is very interesting number, yes? Hmm?
Golden ratio. Golden ratio.
What?
Under root 5 minus 1 by 2 golden ratio, no?
Yes, yes, yes. But if you wish to enjoy a little, you can also construct such a zipper. One, 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 one. Yes. It has 1, 2, 3, 4, 5, 6, 7 copies. This will be 0, this will be 1, this will be 2, this will be 3, this will be... You see, the signature is 0, 0, 1, 1, 1, 0, 0. Yes. And it will give very interesting result. When I saw this result many, many years ago, I understood nothing, but it was surprising for me. Yes. What? Yes, of course. You see, you have 6 minutes. That's enough to build this picture. Hello, hello, hello.